Good afternoon. Welcome to the Faculty Forum Online, a program of the MIT Alumni Association. I'm Judy Cole, the Executive Vice President and CEO of the association, and I will serve as your moderator. Alumni who wish to ask a question, please enter your name and your location and your question in the form on your screen, and we will try to answer as many as possible. Our guest today is Professor Donald Sadoway. He is the John F. Elliott Professor of Materials Chemistry in the Department of Materials Science and Engineering at MIT. Professor Sadoway's research seeks to establish the scientific underpinnings for technologies that produce more efficient use of energy and natural resources in environmentally sound ways. This spans engineering applications and supportive fundamental sciences, and it has also led him to found Ambri, an electricity storage spin-off that promises to change the entire electric power system. The overarching theme of Professor Sadoway's work is electrochemistry in non-aqueous media. Professor Sadoway, thank you so much for joining us today. And it being March 14th, I have to wish you a happy Pi Day.
Thank you.
And I guess there will be many students who will be happy out there today too, and probably many who will not. Can you please start by giving us an overview of some of the current projects in your lab that really excite you?
Sure. I'm going to come with a few slides, if that's all right.
Absolutely.
So the first one is this collage that shows the lighting, and it reminds us that electricity is tantamount to modernity, and that's why I'm so passionate about electrochemistry, because in the end, everything that we think about as 21st century is based on electricity. And you can see that in some spots there's no light, and that means either nobody lives there or it hasn't been electrified. And from my perspective, there's no greater gift you can give people than access to reliable electricity. So I've been working on storage, because storage is the missing piece for sustainable renewables. Photovoltaics and wind are both intermittent, and because they're intermittent, they can't be by themselves fully integrated into the grid, and storage that's the holy grail. So this is the liquid metal battery. It's something that I invented here at MIT about 10 years ago, working with a team of students and postdocs, and it's now the basis for a startup company here in Cambridge, and so there's plenty of work still to do. I thought I invented a battery. In fact, I invented a battery field, and there's so many variants of this that we continue to do research, not just variations on this theme, but I mean major discoveries. And then the other area is metal production. The number one anthropogenic industrial source of CO2 is steel making. And so how do you make steel without, it's about 1.6 billion tons last year, and every ton of steel you produce about 2 tons of carbon dioxide. So I've got a way to produce steel without using carbon, and surprise, surprise, it's electrochemical. And so I could imagine using sustainably generated electricity to convert iron oxide into iron, and so that's the other major area. And this also has resulted in the spin-out of a company. It's called Boston Electrometallurgical, and that company's about 2 years old and has scaled up to make a reactor that can make tonnage metal. And that's it in a nutshell, I think. Yeah. Oh, I have this one last image. It's the old 10,000 lira note with the image of Professor Alessandro Volta, to remind us that electrochemistry began at the university by a professor, and that Volta gave us the birth of electricity, and also the birth of electroplating, electroforming, all sorts of electrochemical technologies. And in addition, proved to us that there is some utility in a professor. That if you give professor resources and students and leave him alone, he's liable to produce something of societal value. So I'm going to leave it there.
Maybe we'll get your face on a U.S. dollar someday when you've
Oh yeah.
found that holy grail of
Okay.
storage for the solar and wind generation of electricity.
Hope so.
Thank you. As we sort through the questions that are starting to come in from alumni, let me ask you one of my own first. I'm sure you've heard the motto of Silicon Valley that, failing fast is important. It seems like finding the best materials for a liquid metal battery involved a lot of trial and error. Do you subscribe to that maxim, fail fast?
I would phrase it a little bit differently. I would say learn fast. It'd be better to succeed fast, but there will be hiccups because, at MIT we try to maximize our determinism and minimize the empirical thrashing. But when it comes to liquid metals, there's the predictability isn't what it is in, say, solids and gases. So there is some empiricism. But I would say learn fast rather than fail fast.
I like that one better.
Yeah, me too.
So another question that I have is, you are perhaps best known among alumni for your teaching of the Introduction to Solid State Chemistry, or 3091.
Right.
A course for which you gave your last lecture in 2010, a while ago. Talk about what teaching that course for 15 years meant to you.
Well, it was a fabulous experience for me. I'm a little bit different from some of my colleagues who love their research, and of course we have to do some teaching as well, and they prefer to teach in their specialty area to advanced students. And I chose a different path. I wanted to teach where there was maximum impact, and I reasoned that was in the freshman core because they're not even members of any department. And I really embraced the subject matter of 3091 and felt the importance of teaching to first semester freshmen. So it was more than just delivery of content, but through the TAs and so on, we were actually part of a new support system for the students who were spending their first semester on campus here and adjusting to being away from home and coming to MIT, which is more than just high school to college. It's high-octane college. So there was that. And then for myself, I learned a lot because I had to understand the pedagogy of how to put this material across to an 18-year-old first-time learner who is really smart but hasn't seen some of this stuff before. And I found that my research trajectory went up noticeably as a result of teaching this class, because I had a more panoramic view of chemistry that I had before. So I learned a lot by teaching that.
Well, and I imagine too that perhaps the uninitiated asks questions that reveal different things about the chemistry than somebody who knows enough to know that really doesn't make sense or something.
Yeah, that's
and so
correct.
It stretches you in that way as well.
Absolutely, absolutely. And it also stretched the ability to explain, because you read the textbooks and they're all pretty much similar. But at this point, what happens is that you find that you have to have a different way of explaining it to make sense to the first-time learner. So I learned a lot.
Yeah.
And I hope the students did too.
Well, and I think it's also really important for the first semester students to see some of the most accomplished and legendary teachers at MIT. If you only get to those people after you've been here for
Yeah.
a few years,
Right.
it could be a very different experience.
Yeah, well, and that's one of the things, I think, hallmarks of MIT, that we do put senior faculty who care about teaching into the first year, whereas in many of the other schools, you can end up with either junior faculty or, in some instances, a TA.
TAs, yeah, exactly. So we have some questions here from our alumni.
Okay.
So let's turn to those. Sheffy in New York asks, you've said that in creating the liquid metal battery, you weren't just looking for a new chemistry, but a new platform. Explain what you meant by that, please.
Well, the concept of the liquid metal battery is 3 layers: a liquid metal, low density liquid metal on top, high density liquid metal on bottom, and molten salt electrolyte in between. That's the template. So now, which metal goes on top? Well, there's a plurality of choices. You can choose anything from the northwest part of the periodic table, where you have the most electropositive elements, and then for the bottom metal, you're going to choose one of a plurality of weakly electropositive elements down from the southeast part of the periodic table. And what we learned was that different combinations of metals led to different performances, and some batteries need to be more nimble than others. Other batteries need to be, say, the analogy is some of them have to be sprinters and some of them have to be marathoners. And so you have the freedom to choose different combinations of metals. And it's not just pure metals, it's alloys. So now you've got multi-component alloy on top, multi-component alloy on bottom, and what are you going to use for the salt? And so this is what I mean by platform. It sort of unlocked this entire world of opportunity, much in the same way if I said, well, I've got 2 solid electrodes soaking in an aqueous solution. Well, there's a plurality of choices for that too.
Thank you. So Alan in Cambridge asks, how has the price of oil affected your lab's ventures in the corporate world? Has it affected research funding too?
The price of oil has definitely affected some corporate spending, although I'm happy to report that one of our first major supporters was the French energy company Total, which came to me via the MIT Energy Initiative. And Total has remained a staunch supporter through all of this. So I think they really see the value and understand the long term. Yeah, it's fine.
Well, and I think that I have to imagine that oil companies, as they see carbon fuels becoming more and more controversial, are looking to other kinds of energies that they can supply. And this battery, developing a liquid metal battery is the key.
That's correct. And I mean, that's what got Total interested in the first place, because already by, I think, around 2007, they had seen themselves not as an oil and gas company, but as an energy company, and they were starting to make investments into solar, and then they realized solar without storage is incomplete, and they looked at what was out there in storage and found nothing appealing, and then came upon my fledgling work on liquid metal and said, let's put some money on this.
That's terrific.
Yeah.
Tom in Minnesota asks, can you comment on the thermal energy storage phase change salts competition to your technologies?
Phase change is fine. I mean, I don't view any of these as competitors. I view them as collaborators. The energy storage market is huge, and it would be like somebody who works at Ford being questioned. I just saw somebody driving a Chevrolet. What's up with that? It's a huge market, and it's not battery versus battery or battery versus thermal. It's battery versus combustion. And so if people can render a practical solution that involves thermal storage, I'm sure it'll find applications. It's not one size fits all.
Now that makes a lot of sense. David in Ohio asks, I believe you were working with developing battery storage technology using common and readily accessible materials. Can you give us an update of your progress? Will the car's body parts one day be the battery itself?
Okay, so now we're jumping topics. The liquid metal battery is for stationary storage. It's not going to go into a car because it has no membrane, no separator, and so in acceleration and deceleration, you'd end up mixing the metal and essentially discharging the battery. I have worked on batteries for portable applications, and the question there is, how far can that go? And that's a former student of mine who has another startup company called Solid Energy Systems, and he's on the road to producing a solid state lithium metal battery. And the hope is that that could someday go into the body of the car. Instead of having a giant battery compartment, you could put the battery in the fender and the cowl underneath the roof of the car. But we still have a ways to go on that one.
Thank you. Bill in Arlington asks, pump storage of water is a cost-effective energy storage solution. If you have a convenient mountain or mine to pump water to or from, I'm wondering if there are analogies to be made with hybrid battery approaches. What additional field gradients are available to store energy via pumped ions, and are there benefits in power to be had?
Yes, pumped hydro is fantastic, and it in fact is the only major deployment of storage, but it's geographically constrained. I mean, pumped hydro isn't going to help us in downtown Boston or downtown Manhattan. So the alum raises some really interesting questions about combining field effects, and I've been thinking about this a lot because I think that we just haven't been using our imaginations enough to figure out ways to harness energy. You know, if you've got an electric charge in motion, you're generating a magnetic field, and you know, why aren't we, trying to combine all this stuff? So don't worry, I'm thinking about that.
Well, Bill in Arlington may want to come talk to you about it some more, too.
I welcome the input.
David from Framingham asks, please bring us up to date on the progress of Ambry, the company you started in Cambridge. I wanted to ask you earlier also, how old is Ambry? When did you start that company?
Late 2010, okay. So
Okay.
it's almost 5 years old.
Mhm.
So it's on the way to deployment. It's locked in on a chemistry that we invented here at MIT about 4 years ago. We've developed the power electronics, the battery management system, and the manufacturing. And there's a manufacturing plant out in Marlborough, Massachusetts. And we're on the road to building the first major battery for commercial installation, and that'll be on the Hawaiian island of Kauai for Hawaii Electric to be used in conjunction with solar. There are still a few manufacturing hurdles to overcome. Nothing with the electrochemistry. I'm happy to report that the electrochemistry works better than we imagined. We're measuring fade rates that are so low that you could discharge this battery fully every day for 10 years and still have over 99% of its nameplate capacity.
Wow.
But there are still a few features on the battery pertaining to high temperature seals that we have to surmount, and then we're off. So I'm hoping that by this time next year we'll have deployed the first batteries in Hawaii.
That's exciting.
Yeah.
So I think you sort of anticipated the next question, which is what obstacles stand in the way? Miriam in Acton asked, at Ambry's plant in Marlborough, you're working now on automating the processes to aggregate many cells into a large format battery. What obstacles stand in the way? And I think you just answered all of those. Right?
Yeah,
Most of
it's
those.
the main obstacle is robust dielectric seal, because as you know, if you drop multiple batteries into a flashlight, they connect to one another by direct contact. So that means the pin on the top of the battery is of different polarity from the body. And we have the same. The difference is that our battery is running at about 475 degrees centigrade, and so that insulating seal has to satisfy a number of constraints, including coefficient of thermal expansion to match with the metal of the container, which is steel. Has to be dielectric, very insulating, and also has to be resistive to the vicious metal that's in the head space above on the top of the battery. So we can build this to a NASA price point, but that's not good.
I understand. So Keith in Boston asks, what are the advantages and disadvantages of low melting point metals or alloys versus high melting point metals or alloys in the liquid metal battery?
Well, the lower the operating temperature, the greater the round trip efficiency, because the battery has to keep itself molten. So that means that some of the electricity is used to generate heat. And even so, with this battery running at 475 degrees C, the round trip efficiency is over 75%, which is compares favorably to pumped hydro, which is around 70%, because pumped hydro is electrical to mechanical and then mechanical back to electrical, so the losses are high. If we could get a battery that would operate, instead of at 475, say 275, well, then all sorts of other things start to happen. We don't have to work in steel. We could work in polymer cans. The seals problem would be trivialized. The interconnects, you can't use pure copper for interconnects at 500 degrees C, so we have to use certain special alloys. So the round trip efficiency goes up, the cost of production goes down, and the service lifetime goes up. So there are compelling reasons to drive the cost down. But to make the point, there are plenty of low melting metals that'll work. The bottleneck is the salt.
Oh.
The salts, because these are ionic compounds, they're high melting. So actually that's a new frontier for us, is developing low melting practical salts. We're not going to turn to ionic liquids because those things are frightfully expensive and they have abysmal conductivity. But I think that there's some room for discovery there as well.
Fascinating. Paulina in Newbury, Mass. says, is a liquid metal battery better suited for a certain type of intermittency?
The answer is no. What we've found is that this battery can operate in multiple markets. So it can operate in the long-term market, which would be shifting the demand from high peak to low peak, so that at 2 a.m. when the demand is low, you could take electricity from a conventional generating facility and send it into the basement of a skyscraper in downtown Manhattan, and then at 2 p.m. you pull that energy out. So that would mean you don't have to build a new power plant, you don't have to build new transmission lines. But then the battery can also work in the high-speed applications, such as frequency regulation, where if supply is out of balance with demand on the grid, then you're in trouble because there's no inventory.
Yes.
So if
Heat wave in Manhattan in August.
if supply is out of balance with
Yeah.
demand, what will happen is that the voltage will migrate and the frequency will migrate, and you'll blow your devices. So sometimes the remedy for frequency regulation isn't more electricity, it's to dump electricity. And so that battery can act as a load, it can act as a source, and it can also be playing in the market of off-peak shifting. So it has a number of attributes that it can
It's
play.
like it's almost like a shock absorber between.
Yes, that's a good analogy. Yes.
So David in Columbus asks more about the temperature. Since liquid metal batteries operate at elevated temperatures and require heat energy input, how much net energy output does this type of electrochemical approach provide?
It's a 75% round trip efficiency. So that's accounting for the heat, and that's on a cycle of 4 hours discharge, 8 hours idle, 4 hours charge, 8 hours idle. Round trip efficiency above 75%.
And Robert in Los Angeles, you intrigued me with your northwest-southeast description of the periodic table for elements of liquid metal batteries. Please explain the chemistry of how your battery works.
So the element on the top is the strongly electropositive metal, something like magnesium, and the metal on the bottom is a very poor metal. So you put a really good metal opposite a really poor metal, but not a non-metal, because non-metal is not going to be electronically conductive, and then you're going to have all sorts of other facilities in place. And that's the weak point about sodium sulfur. It works, but sulfur is an insulator, so you have to impregnate the sulfur in a graphite matrix and so on and so forth. So one of the worst metals I can find is going to be a semi-metal like antimony. So antimony goes on the bottom, and mercifully nature was kind here. Magnesium has a density of less than 2, antimony has a density of greater than 6, and the molten salt, which contains magnesium chloride, has a density of about 3. So they lie one on top of the other in the right order. And the magnesium is insoluble in the salt, and the salt is insoluble in the antimony. Magnesium wants to alloy with antimony, but it's insoluble in the salt. So the only way I can get to the antimony is to become magnesium ion. And so when it becomes the ion, it dumps its 2 electrons, they go to the external circuit, magnesium ion goes across, becomes a neutral, and alloys with antimony. So the top layer gets thinner, the bottom layer gets thicker, and the salt layer remains the same thickness, but it moves up in position. And then to charge the battery, we force current through it and bring the magnesium back to the top layer, and thereby purify the magnesium and purify the salt. And that's the secret in how the thing lasts so long, because every time you charge the battery, you essentially return it to its pristine condition.
That's really quite elegant.
Yeah, I think so.
So Julie in New York asks, speaking of New York, where do you see the biggest energy strains on the existing grid as populations continue to grow here or in the developing world? How desperate will we be for this technology in 10 years?
There's going to be various forms of desperation. Right now, Hawaii is our first customer because Hawaii imports diesel fuel, burns it, and makes electricity at 43 cents per kilowatt hour with a superabundance of sun and wind. So there the pain point is high. The calculations are that with the liquid metal battery and photovoltaic solar, on day one, without subsidy, their electricity rates would drop to 26 cents a kilowatt hour. So this is not being implemented because it's green and it's the right thing to do and so on. It's being implemented because it's cost effective. Now, in Manhattan, the looming problem is the growing demand for electricity, thanks to the insatiable appetites of servers in the financial district and the growing use of mobile electronics and whatnot. And then if we see more and more use of plug-in hybrid electric vehicles, the demand for electricity will continue to rise, and there's plenty of generation capability in the New York area, but not on the island of Manhattan. And at some point, very soon, the capacity of the transmission lines will be exceeded. And that means you can't send the electricity. Even though you have it, you can't send it, because if you raise the current any higher, you're going to melt the wires or melt the insulation or both. And to install a new transmission line, which is going to have to go under the Hudson River or the East River, it's probably $1 billion expenditure. So being able to avoid the construction of a new transmission line is worth a lot of money. And then Judy says about the developing world. In that first image I showed, you can see darkness on that image. Instead of making a conventional grid, you could have solar arrays and batteries either at the solar arrays or deployed nearer to the end user. And then you make it possible to draw electricity from the sun even when the sun doesn't shine. So that's the gift of electricity.
Yeah, I see what you're saying. And the Manhattan one, I hadn't really thought about that, but storage is the answer there.
That's right.
Maddie in Texas would like you to please talk about your conversations with Elon Musk and his firms. Will industries like Tesla, Solar City, etc. produce the next greatest research in this field, or labs like yours?
I have not had any conversations with Elon Musk or his companies.
You didn't get to meet him when he was here on campus?
I didn't.
Wow.
I didn't. But that's okay. You know, his primary focus is on automotive applications. Parenthetically, they've thrown in the Powerwall. And as I said earlier in response to the question about solar thermal storage, it's a big market, and anything that can help the customer be able to deploy sustainable renewables is fine with me. But let's not forget that Tesla is in partnership with Matsushita Panasonic, and they're deploying today's lithium-ion batteries. And so if the question is, where is the next technology going to come from? It's not going to come from the battery industry. The battery industry is capital intensive, very conservative, and in fact the lithium-ion battery itself, the genesis of that was Sony. Sony needed batteries that were higher energy density so that in the early 90s their next generation of Walkman and Handycams would have a longer runtime. And there was a researcher at Sony Labs who came upon John Goodenough's discovery of lithium cobalt oxide material and reasoned that he could put that lithium cobalt oxide opposite some carbon and have what was called a rocking chair battery. It's lithium ion because there's no lithium in it. The lithium runs and hides either in the carbon on the negative or in the lithium cobalt oxide on the positive. And this was 1990, and Sony went to all of the big Japanese producers. Remember, China was an isolated communist country then. Japan was the mighty tiger of the East. And they went to all the big battery companies and said, look at this chemistry. This is fantastic. It's 50% better than nickel metal hydride. Every company said, no, we refuse, because we've got all this capital invested in nickel metal hydride. So Sony took the unprecedented step of saying, well, I guess we're going into the battery business. And then the cell phone people said, I want that. And the laptop people said, I want that. And nickel metal hydride was mowed over. And so it's going to happen again, just as the change in imaging didn't come from Kodak. So the answer to her question is, it's most definitely going to come from the university.
Yeah, from labs like yours. May in Newton, Mass asks, when lithium-ion batteries first appeared in cell phones, we all loved their durability. Talk about why this technology is insufficient for personal energy purposes.
So the cell phone has a service lifetime of about 2 years. About every 2 years, your contract is renewed or up for renewal by your service provider. And that's about the duty cycle for phones. About every 2 years is a next generation phone. In those last several months, you may be cursing your phone that you don't quite get through the day, depending on what your use pattern is. If you use it for just making calls or something, it's okay. But if you're using it intensively as a handheld device for web-based activities, you might find that towards the end of that 2 years, it's not good enough. If you put that same battery in a home, do you want to be replacing your lithium-ion batteries in your home every 2 or 3 years? Do you know of anybody who has a 10-year-old telephone with the original, the OEM battery in it? So there's a major difference in use patterns and service lifetime. So that's why copy-paste, just make them big, or the Tesla approach is to continue to use the little 18650. It's 18 millimeters by 65 millimeters. It looks like just a little bit larger than a double A, and they put 6,000 of those in a Tesla. Well, if you want to make a say 2 megawatt hour, say 1 megawatt hour. 1 megawatt hour would be about the size of a 40-foot shipping container. That would require 93,000 18650s. If I gave them to you for free, somebody's got to assemble those and wire them, and then of course keep them cool, because if the temperature rises, you'll have a fire. So that's why that chemistry it's fantastic for small mobile devices and served us well. I'm even a little bit skeptical about its use in all electrics. I mean, yeah, you can sell a car to a Tesla price point and make it work, but if you can afford a car for $150,000, you throw it away in 2 years because the ashtray is full. You know.
So Tom in New Hampshire asks, he says, most people get worried when they're jump-starting one car with jumper cables. You and your team are working with chemicals at high temperatures to discover new phenomena. Were there times you felt insecure about where an experiment was leading?
No, I was never feeling insecure. I understood the chemistry, and it's fine. We actually had unplanned, I might add, the worst case scenario where somebody dropped something and the top electrode made contact with the bottom electrode, and so they mixed quickly, and we got a huge exotherm. But the temperature maxed out at a value that was below the boiling point of anything inside the battery and below the melting point of the case. In fact, I once had a couple of fellows from DARPA come to visit me, and they said, can you imagine putting this battery at a forward operating base, say in Afghanistan? And I said, sure, you can put it. And they said, what happens if a sniper's bullet penetrates the battery? I said, well, the bullet will alloy with the magnesium on the top or the antimony on the bottom. And he says, yeah, but now it's got a hole in it. Now it's leaking liquid metal. I said, yeah, the metal will freeze. And they look at each other and they say, battle hardened. So oddly enough, a battery that operates at elevated temperature is safer than a lithium-ion battery operating at room temperature.
Very interesting. Very interesting. We have only a few minutes left, so let me ask you just two more questions.
Okay.
Can you give us a sense of the breadth and depth of pursuits in which your former graduate students in the energy field are now involved? That's the first question. And then the second one is, can you talk about you and your team, talk about support you and your team have received from MIT's innovation pipeline, e.g. MIT, the Deshpande Center, etc.?
Okay, so the first question was about
breadth and depth of your graduate students' pursuits in the energy
they're
field.
all over. They're all over. They some of them are working at Ambry. So they're on the tech side and deployment of technology. I have some students that one of them went on to he worked for the EPA at their automotive test lab in Ann Arbor, Michigan, and now is working for the National Natural Defense, what is it, NSRDC, I forget what the acronym stands for. It's an initialization, it's not an acronym, but
Right.
he's in San Francisco at their main office. Another fellow is working at Toyota in Washington, D.C. So they're in government, they're in regulatory agencies, they're in technology.
They're all over the map.
All over the map.
Well, that's great to hear. And what sort of support have you received from the various entities around, like Mighty and
Yeah.
Deshpande Center, things like that? Did
So,
they help you with your
absolutely,
company?
absolutely. The Deshpande Center gave me the first money in for the very first attempts at building this liquid metal battery, and then through Mighty, I came in contact with Total, which gave me the first major money, and then along came ARPA-E, and I was a first-round winner of ARPA-E funding, and having all of these various organizations present at MIT was enormously beneficial. I don't think I could have got this, because the liquid metal battery sounds great right now, but back in 2005 when I was proposing it, the world was really so wedded to lithium ion and fuel cells. And so people looked at this and said, "No, this is crazy, it's not going to work, it's high temperature, the round trip efficiency is going to be abysmal, there are going to be safety issues," and so on and so forth. And it was the Deshpande Center that was willing to take a chance on a radical idea, and I'm eternally grateful to them for taking the chance.
Well, that's the beauty of the MIT ecosystem.
It is. It is. It is.
Absolutely.
They're you know, because when you look at radical innovation in capital-intensive industries, people get wrapped around the axle of risk. Well, I can't give you radical idea and zero risk.
Yeah, right.
So
That's not how you advance things.
If you want to guarantee zero risk, go work on lithium ion. You'll work on incremental improvements. Guarantee you'll have lots of successes and zero impact. Just saying.
Well, that's a wonderful note to close on, and I thank you very much on behalf of the Alumni Association, Don. This has been a really fascinating conversation. And thanks to our alumni viewers for asking some really wonderful questions and teasing out all of this delightful conversation. If we didn't get to your question, we will be passing all of the questions we've received on to Professor Sadoway after the webcast. And please continue to share other questions or comments on Twitter using hashtag MIT Faculty. You can also view an archive of past faculty forums online by visiting the Learn section of the Alumni Association website. Please join us next month for another session of Faculty Forum Online.